From last lecture. So now this is a combination of convection and diffusion problem. So when you have a physical situation like this, it's a typical fin problem. Okay. At the base, the temperature equal to 500 degrees centigrade. Okay. So here, this is an insulated end. I mean, this phase, insulation means what happened? The temperature gradient is 0. Good. The temperature gradient is 0 at this insulated. Okay. So here we have to focus on, due to the temperature difference, the convection rate also playing. So the T infinite has been given 20 degrees centigrade. Last semester you have seen in the heat transfer subject. So last semester we have solved an analytical method. How can we solve the how much of convection heat transfer coefficient is playing? Due to the convection heat transfer coefficient, there is a heat transfer. So directly we can get by using an analytical method. Now the same problem, how to solve? By using a finite volume. Okay. So this physical situation, so it gives an equation as, so it's a one-dimensional AA dt by dx minus, I said this is a combination of convection and conduction. So the convection quotient HA T minus T infinite equal to 0. This is given by a mathematician. Okay, in your problem they are given. Not, you cannot directly write it. Okay, this situation gives this equation. Okay, this is a convection term, this is a diffusion term. Okay. So now we will apply this equation into a finite volume and integrate over the control volume, we will get numeric. So first step is, I have to discretize the domain. Okay. So you can consider length is 1 2 meter, you can consider it's 2 by 5. You can consider L equal to 2. Okay. And n square equal to 25. What's meant by n square? This is HP by Ka. These are the physics, okay, in the heat transfer. These are the given in your problem. These values are given in the problem. Then an atmospheric temperature or ambient temperature, the insulated end is, and corresponding base temperature. Another name is, this is a base temperature. Okay. So this is a TB equal to constant. You mean this end because of the insulation. So when you discretize this 5 control volume and corresponding node, I know a temperature at this location, I have assumed 500 degrees centigrade. Okay. This end, the gradient have been given, rho T by rho x equal to 0, this end. Again you have to integrate this equation on each control volume. We have a 5 control volume, 2, 3, 4, 5 control volume. So first, you have to convert this equation for interior node and treat the boundary condition separately. Because of, there is a noun values and we have to manipulate separately when dealing with the control volume 1 and 5 as usual. So discretize the domain. After you have to integrate. Before integrate, I need to convert n square. So when I divide by Ka, I will get a n square. It's not H, it's P. Okay. So divided by Ka, I will get dt by dx minus hp by Ka equal to n square. T minus T infinite equal to 0. Okay, now integrate it over a control volume. So I can write as due to control volume dV is here. So A of dou T by dou x east to west, and it to be n square A. So particular this T is varying with respect to node to node. Okay, along each node this T is varying, but this T infinite always be constant due to the ambient temperature as given. So this I can write directly Tb. And this is for each control volume. So this contribution takes place on each control volume. Del x also, when you discretize this equation, will appear equal to 0. So you can write this left hand term AE and dou T by dou x east minus dou T by dou x west n square A del x Tp minus T equal to 0. Okay. So when you discretize it, Te minus Tp by del x minus AW Tp minus Tw by del x plus n square A del x Tp plus n square A del x T infinite to 0. So A by del x T Okay. Now you can assemble for a Tp and a AE Te. So Tp I can write as how many Tp is there? 1, 2, 3. Yeah. So area you can assume this per unit meter square, 1 unit square. Okay. So 1 by del x. 1 by del x minus n square del x. Okay. Equal to it's also minus, is it? You can write this as a plus. You have to send everything on the right hand side. Now better. And 1 by del x plus 1 by would act as a source term because of everything now. N square has been given, area also given, del x we have to fix 2 divided by 5.4 and t infinite also given. What's the value around? Two? $5,000. Okay. And for this is a generalized equation. Again, it has a form ATP equal to AETE plus AW TW act as for the source term. Okay, it's a generalized form. In the first lecture, in the finite volume, we have wrote. It's a one dimensional. If it is 2 dimensional and A north T north plus A south T south. Again, when dealing with the 3 dimensional, after completion of this problem, I will derive it separately. For node 2, how can I write it for node 2? So what about AP and AE, AW? Del x value is, what's the del x value? 0.4. 1 by 0.4, 1 by 0.4. Substitute. Tell me the values, Gaussian values. What's the AE Gaussian value? 1 by 0.4 2 AP 2 1.5. Only 15 TP here. 1 by 0.4 border 0.25 2.5. Okay, so we can write this equation at node 2. So 15 T2 2.5 T3 is it plus 2.5 T1 plus 500
5,000 5,000
200
where
200
where
5,000
instead of 200 it's a 25 0.4 20 okay, it should be 200. Now 15 T2 minus 2.5 T3 minus 2.5 T1 equal to 2. This is the equation number 2. With respect to node, you have to give a equation number. Don't give randomly, because of when you assemble in a matrix, it will trouble. So for node 2, it's equation 2. For node 3, T3 and 2.5 T4 plus 2.5 T2. Okay, plus 200. So 15 T3 minus 2.4, 2.5 T4, 2.5 T2 equal to 200. So equation number 3. 15, T4, 2.5, T5, 2.5, T3 plus 200. So equation number 4. Okay. So we have solved this 3 control volume now. Okay. We formed the equation for each control volume. Now, looking your boundary. So for boundary node 1. Okay. The east node. So point 3. This is TA equal to has been given 500. Is it 500? Apply the governing equation. Apply this governing equation directly. Okay. This is a governing equation after discretizing. So there is a east face. Instead of west face, listen, this is not west face. You have to concentrate. Because the TP minus here TA. TA del x by 2 will in the product. So you can apply this equation here. AE T minus TP by del x minus 2 times of A TP minus TA divided by del x, and remaining all same because of convection doesn't vary. Okay. So what about A to be 1 value? So 1 by del x TE minus 1 by del x TP 2 by del x TP 2 by del x TA. Any doubt? Now substitute value here, it's a 2.5, is it? T plus 2.5 TP. So 2 times of 2.5, 5. 2.5 into 20. 500. 1200. 500 left. Huh? 1? 2,500. Like 2.5 into 500.
1250 sir. 1250.
What's the value? Hey.
2,500.
2,000?
500.
So, TP, this value. What about this value? 10. So 10. This is 25 into 10. So this is to be 10 TP. Okay. So 10, 15, 17.5. Okay, minus 17.5 TP. And yeast 1% 2.5 TE. And this is 2700 minus 2000. Okay, va? Minus 17.5 T1 plus 2.5 T2. This is equation 1. So apply the same governing equation at the nodal point 5. Node 5. So look here carefully. So here yeast term, there is a gradient, is 0 because of insulation. So directly you can send to a 0 value. Okay, when you discretize this equation, we will get dou T by dou x at the yeast phase. So this is a yeast phase, our corresponding node, fifth node. So yeast phase having a 0 gradient. So directly you can delete it, and only we have to solve this term, 2 term alone. Okay. Clear? So minus AW TP by Lect plus AW. It's a western node, no need to del x by 2. East only directly they ask to cancel. Gradient. There is no tool. Only western node is present. Now this is 2.5. This is 2.5. This is whatever this 5 are. Is this 5? 10. And this one 200. Is it?
I don't think that.
Which one 10?
Next term.
Huh?
Next term. 10 T infinity.
10 TP, then it's also 10. 200.